Well, in this lecture, I will be talking about CTC loss and inference. So CTC stands for Connectionist Temporal Classification and deals with problems in a very different way. The intuition is to output a single character for every frame of the input, so that the output is the same length as the input, and then to apply a collapsing function that combines sequences of identical letters, resulting in a shorter sequence. So we have alignment here. We have input, but we have alignment, and then we collapse it so it becomes the output. For example, the dinner, we align it. For example, this acoustic vector corresponds to I. The next acoustic vector again corresponds to I. But this way has a problem because you know that the spelling of dinner is very different from this one that is appeared here. So you see that it cannot capture the correct words. So dinner is not dinner, as you see here. So there should also be another problem. It doesn't tell us what symbol to align with silence, because we don't want to be transcribing silence as everything. So you need this CTC algorithm. So first we do alignments, and then we merge duplicates. And this is the blank character symbol that I want to talk. This is really interesting because if we just use these blank, then even if we shrink some of these and merge them together, then no problem. So it appears dinner and not dinner. So we don't have any problem like that. So using these blank symbol, you can. It's an elegant idea. We can remove these problems. And the CTC collapsing function is many to one. So now you see there are many ways that result in a different in one particular output. For example, if our y is here, we have three, for example, we have three different ways that we can create such a thing, and so we should create which one is higher probability. Even if we create that we will see that we have a problem, because some of them even may not lead to the final answer if we sum over all of these things. So this, first of all, we should start with CTC inference, that's saying that we make a strong conditional independence here, strong conditional independence. So that our decoder is just simplified to just a simple classifier, is reduced to just a simple classifier, because we are not using any decoder. Our decoder is just a simple classifier because we have used a strong conditional independence. So why not use a simple classifier? So first of all, if we calculate feature computation, we do subsampling and give it to encoder, and then our decoder is just this classifier, simple classifier, to produce the output letter, for example, dinner. And so what is the CTC inference? First, we should sum over all possible things that can happen. And this is not tractable. It's very expensive because there are lots of alignment that could lead to the single y. So there are many a's that result. So it's many of a, many to one. So many of a's leads to just one y. So that's why we are summing over all possible things. Just like if you have seen my playlist for probabilistic context-free grammar, then, for example, in denominator, you should sum, for example, in conditional random field, you should sum over all trees in probabilistic context-free grammar. We should sum over all sum over trees, and this is not tractable. That's why we use dynamic programming in this case. But here again, we have the same kind of problem. We should sum something that is very expensive to calculate. So let's see what we can do. So because of a strong conditional independence assumption mentioned earlier, CTC does not implicitly learn a language model over the data. It is therefore essential when using CTC to interpolate a language model using interpolation weights that are trained on a dev set. So we are trying to improve, reduce our problem of conditional independence, that we ignore many things. So we try to reduce that problem with language model. And this is the factor, the weights, that you see how much language model is important. If lambda is high, it means that you care a lot about language model, and the amount of CTC loss is not important relative to language model. So we sum over, as I said, over all possible alignments and in your data set D. So the loss for our entire data set D is the sum of the negative likelihood of the correct output for each input X. So to compute CTC loss function for a single input pair X and Y, we need the probability of the output Y given the input X. So we need to sum over all possible alignment that would collapse to Y. For example, there are many things that result, many alignments that result the word dinner. For example, Y could be dinner, and there are many alignments that create the same thing. So we sum over all of these things to cover this issue. So naively summing over all possible alignments is not feasible. However, we can efficiently compute the sum. Whenever we have a problem in computer science of summing and those things, dynamic programming could be a good choice. So most of the time, you see that dynamic programming, such as forward-backward algorithm in HMM and CRA, works. And we can reduce the challenge of computing these things, which is very expensive if you want to do it with brute force or do it manually. And that's why, so the original dynamic programming for both training and inference are given in this beautiful reference. And now we are combining, so I explained encoder-decoder architecture in the previous lecture for speech recognition. Now we are adding CTC loss. Now we are adding CTC loss, and two losses, we combine them, and this is enough for training. But for inference, we can combine the two with the language model. For inference, we also add the language model, and which Y is maximizing this. So we will see, for example, dinner, the word dinner, for example, maximizes that. For each pair data set, X and Y in D, in data set D. And it is good for streaming models because streaming models, we don't see the whole sentence at once. It's not offline. We are doing a sequence, letter by letter, so you don't see the future. So future is hidden for you. So here we can use this architecture that we have an RNN, and we can improve the CTC, because now we have we are also summing like before, but now we have hidden variable. Our hidden variable comes from encoder and also the prediction from this language model. So our softmax is combining this, and this is our decoder. So we are combining the information from the encoder and the prediction network. And at the end of the day, you should see if your if your speech recognition model is good enough or not. For example, in language model, if you see my playlist for language model, engrams and those things, we use transformer architectures, and then at that time we used perplexity as a measure of how much you are excited about the next word that is appearing. And now we have a different measure for speech recognition. This is word error rate. So example, the number of insertions is different from substitution. Insertion is mean you don't have something, the goal is very different from what you have predicted, so you have to insert it. But substitution, it means that you have something that you should change it, maybe rephrase it, or I don't know, maybe change that word. And deletion, it means that word is wrong, you should delete it, because we don't have that in the goal answer. So, and also, normalized by the total words in the correct transcript. For example, here word error rate is 76%, which is very high. So it's almost wrong. Reference is very different from hypothesis. And so this is I stands for insertion, S stands for substitution, and D for deletion. For example, here we have substituted a lot, substitute, form of, stores, and insertion. We have inserted this portable form, and in the next lecture I will talk about text to speech, which is the opposite of speech recognition.